Alright, so next bit, rather than trying to find the roots and the zeros, we want to go the other way around. Based on or given roots or zeros, we want to be able to find equations that match the criteria for having those roots, or find expressions or functions that match the criteria given the zeros that were afforded. Now with these, we can do it, but there's one thing to keep in mind. There are infinitely many equations and infinitely many functions and expressions that satisfy having these roots or satisfy having these zeros. But we deal with it in a particular way. Now if we have a look at this guy over here, we have roots at z equals 5, and then we have these complex roots over here, 2 plus or minus 3i. Now, if I said, can you make me an expression that has this 0, what would it be? It will be, I'll get rid of that because we're doing expression. It's a 5. What expression would have a 0 at 5?
Negative. Z take 5.
Yeah, z take 5. Because if we substitute 5 into z, then the whole thing's 0. Now, this is our linear factor here. The next thing we need to do is we need to figure out what would our expression be if this was a 0 here. I'm just going to get rid of this because we'll do some working out above. Do you remember the sum and the product method for finding equations? So the sum is equal to alpha plus beta, and then this is the tricky bit. You put a negative in front of it. Why? We'll get to it in a moment. And we've also got the product, which is alpha beta, but it's also got a double negative, so we just get rid of the two negatives altogether. If we can find the sum and the product using our zeros at 2 plus or minus 3i, then we're able to construct a quadratic expression. Using the quadratic expression, we combine it with this linear factor here, or this linear root over here, and then all of a sudden we have the base expression to build our equation. So starting off, let's just assume that alpha and beta, so alpha is 2 plus 3i, and beta is going to be 2 minus 3i. If we do this expression over here, we're going to get negative. Our alpha will be 2 plus 3i. Add 2, take 3i. When we combine these together, it's a difference of two, oh no, sorry, not difference, it's the conjugates. So when we're adding the conjugates together, the imaginary part goes bye-bye, and we're just left with negative 4. So there's our sum. On the other hand, our product is going to be 2 plus 3i, 2 take 3i. This is going to be the difference of two squares situation, so we get 2 squared plus, not plus, take 3i all squared. This becomes 4. This is going to become plus 9, so that's going to be 13. So there's our product. So if we put this together, the expression with the zeros 2 plus or minus 3i is simply going to be z squared take 4z plus 13. Do we agree?
Yeah.
All right. Now the second part, there was a 0 or a root at z equals 5. So as explained before, we're going to get z take 5. And here's our expression, but remember we don't want an expression. What are we looking for?
Equation.
Equation. Now, that would almost get you full marks. Do you remember when I said there are infinitely many expressions and equations? Have a look on the board here. If we have, let's see if it likes doing Z. Okay. Here's an equation. Z squared plus Z plus 0. If I put in the 1 we have on the board, which will be Z squared take 4Z, plus 13, and then it's Z take 5. Let's get rid of the lines. Alright, here's what we look like. We only cut the x-axis in one location on the real plane. If we expand it to the imaginary plane, then we're going to cut it again. Now, if I add a scaling factor of, or a dilation factor of A, have a look what happens when I scale A up and down. Are we actually cutting in different locations? No, we always cut at the same place. So because of that, by adding a dilation factor of A, we have infinitely many equations with common roots. So as a consequence, what we have to do when we're working with these is we have to define A in front, and then we're going to say where A does not equal 0. And what that communicates is A is any real number that's not equal to 0. Cool? Awesome. Alrighty. Next one. Hopefully that's visible. Alright, what we want to do is we want to up the ante, and rather than having an equation that's order 3, we're going to order 4. Now constructing this, we've got roots at 2 over 3, minus 4, and minus 2, plus or minus 3i. If we get rid of this one over here, that would be easy pickings because it's the same as the first one we did. However, the 2 over 3 changes things a bit. Could you tell me an expression that has 2 over 3 as a 0?
3 take 2.
It will be Z take 2 on 3. Yep. Alright. We're going to change this slightly. I don't like having fractions in my linear factors. Why?
It's ugly.
I don't know. The other mathematicians told me. And it's ugly. So how can we stop this from being a fraction?
3 take 2.
What could we factorize out of here?
3.
What? Yeah, we factorize out a type of 3. What would I multiply this by to get rid of its denominator?
3.
We multiply it by 3. So let's multiply this by 3. It's going to be 2, it's going to be 3. What is the consequence of doing that? How do we make it so that this value doesn't change? If we multiply it inside by 3, what must we do outside?
Multiply it by 1 and 3.
Bingo. So there's our linear factor right there. Not pretty in my perspective, but that's what we do. Okay, next part. The next linear factor is going to be Z take or plus? Plus. And here's the baseline for our expression. The next one's going to be, we'll put an A up here, and then over here it's going to be Z squared plus, we'll say capital B for now, BZ plus C. Whatever that is, we're not sure yet, but this is going to be our equation. What we need to do next is we need to find what goes in there. Do we have a method for that?
Yeah.
Of course, we've already done it. Oh, it's the same as before. Alrighty. Cool. Do you understand why we have the negative here but not there?
Yeah.
Why do we do that?
Because if you expand it out, you get the two negatives and then count them together.
Yeah, so the idea is that these are actually the negatives of what we would be, where is it? They're actually the negative versions of what we have here and here. So that's why we get the negative. You factor out the negative over here on the alpha and the beta. And on this one, it's double negative, so negative alpha times negative beta, which is just positive. In the book, they, where is it? In the book, they just say that's always a negative, but if you deal with it sooner, I find it's just easier to remember. Cool.